And now we move on to Kevin Wilson. Now, Kevin is lecturer in statistics at Newcastle University, and his title is Uncertainty, Elicitation and Quantification from Experts. Off you go. Thank you, Kevin.
Thank you very much, Phil. I'll just start my timer so I know how I'm doing for my time. So just a quick overview of some of the things I'm going to say. So I'll start off, I'm not an expert on infectious disease modeling, but I'll start with infectious disease modeling to try and motivate why we might want to do expert judgment elicitation. I'll then take a step even simpler from the sort of things that Willie was talking about, and I'll think about, well, how might we elicit from an expert, a single unknown, and I'll spend a fair amount of time on that, and then I'll move on to the sorts of problems that Willie was talking about, where I have a single unknown at a time and I've got multiple experts and I want to combine their expertise into a single distribution. There are some slides on elicitation of multiple unknowns, sort of eliciting model structures, Bayesian networks, as Willie touched on there. I probably won't get to those, but the slides are there and people can look through them in their own time. And then at the end, I'll try and close the loop and come back to see how the sorts of things that I've been talking about might impact on infectious disease modeling. So that's what I'll try and do. But let's start off with thinking about mathematical models. So as we've seen, mathematical models have had quite an important role so far in the COVID-19 pandemic. Certainly in the UK they have. And in particular, the most influential mathematical model probably so far was in this report by Neil Ferguson's group in Imperial, where they looked at the impact or the potential impact of non-pharmaceutical interventions to reduce mortality and healthcare demand. And in particular in this paper they had a micro-simulation model. So essentially they simulated millions of people going about their daily business, and some of those were infective, some were susceptible, and they tracked the potential spread of the disease based on certain scenarios, and those scenarios were certain government interventions in order to try and reduce or mitigate the spread of the disease. And this this report is certainly thought to be part of the reason that the UK government seemed to change from a herd immunity type approach to actually trying to stop the spread of the disease and moving to lockdown and those sorts of actions that they took. And of course, in this micro-simulation model that they used, in order to run the simulations, they needed to specify lots of different model parameters. So there are lots of input parameters that needed values in order to run these simulations. So here's just a few, and this is in no way meant to be a critique of their paper or of their model. It's just an example of the sorts of things that modelers need to choose in models. So for example, they had to assume an incubation period and they chose 5.1 days. They had to pick what percentage of hospitalized individuals would require critical care. They picked 30%. They had to choose a value for the R0 parameter that Willie talked about. They chose 2.4, but they did a little bit of sensitivity analysis on that in the simulations that they did. And probably the most relevant sentence in the report from our point of view, or the point of view of the talks today, is that they said at one point, based on expert clinical opinion, they assumed that half of those in critical care will die. So from this, because of course we have a very fast moving situation, we're trying to essentially model things in real time as the pandemic is occurring, then there won't always be large quantities of high quality data available in order to specify these input parameters to these mathematical models that we're trying to use to make decisions about the pandemic. And so some of the time we're going to have to rely on other information other than observed data. And in that case, one of the things that we might want to lean on, as Willie talked about in the last talk, is the opinions, the judgments of experts, the knowledge that experts have about these sorts of things. So let's think about this, the simplest situation that we could perhaps come up with here. We have a single unknown, one of these inputs to a mathematical model, and let's call it theta. And we want to specify a value for that unknown theta in our model. And let's suppose that we don't have a very large quantity of high quality data, and therefore we've decided to ask an expert in order to provide us with a value for theta, the parameter, this input parameter, this model. And so what we want to do is we want to somehow get at the expert's knowledge about likely values of theta. but also about their uncertainty. So what values could theta take? What values would this expert rule out, essentially? So essentially, we want to encode this expert's knowledge and uncertainty about theta. And how might people do this? Well, in the classical method that Willie talked about, and in fact, in lots of expert judgment contexts, typically what people do is they ask for quantiles of theta. So the technical definition of this is that the 100 alpha percent quantile of theta is the value for which the probability that theta is less than or equal to this quantile is equal to alpha. And we have to choose Q in that equation there. So perhaps that's a little bit too abstract. So let's think about a slightly easier one. So the median, which is the 50% quantile, would be the value for theta that the expert thinks it's equally likely that theta is above or below that value. So in some sense, it's their best guess about the true value of theta. And in order to get at the expert's knowledge and their uncertainty, we might ask the expert for 3 quantiles, or perhaps more or perhaps fewer, but 3 is a number that's often used. And why do people use 3? Well, if you've got 3, then you can ask for a best guess. So for example, a median. And then you can get an idea of the range of values that the expert thinks is plausible. So I could ask the expert for a quantile below the median and a quantile above the median, and that gives me an idea of the plausible range of the value of theta in the opinions of the expert. So this is the sort of things that people do. And then, of course, we then have 3 numbers, and that in some sense represents the expert's knowledge about theta, but they have uncertainty about it. How do we represent uncertainty? Well, the only sensible way of representing uncertainty using a number is to represent it with a probability distribution. So we'd like to use these 3 quantiles we ask the experts for to define a probability distribution over theta. So how easy is this? Well, let's have a look at one example. There's 2 on this slide, but let's just take the top one. So if you've got a piece of paper and a pen in front of you, perhaps you could have a go at this. So if you could provide your 5% quantile, your 50% quantile, and your 95% quantile for the distance, and you can do this in miles or kilometers, I've got both, between Glasgow and Edinburgh. So your 50% quantile, your median, is the value that you think it's equally likely that the true distance between Glasgow and Edinburgh is above or below that value. Your 5% quantile is the value below which you think there's about a 5% probability that the distance between Glasgow and Edinburgh is below that value. And the 95% quantile, similarly, you think there's a 5% chance the true distance between Glasgow and Edinburgh is above that value. And so between them, the 5% quantile and the 95% quantile give you an interval in which you think the chance that the distance between Glasgow and Edinburgh is 90% is between those 2 values. So you've given yourself a 90% uncertainty interval for the distance between Glasgow and Edinburgh. And hopefully you've had time to do that while I've been sort of whittering on about it. And if you have, then I'm going to reveal the answer now. So the true distance between Glasgow and Edinburgh is 41 miles or 67 kilometers. And so if you are a well-calibrated audience, if you are good at estimating your own uncertainty, then 90% of you who wrote down an interval there, the true distance of 41 miles will be between your 5% and 95% quantiles. So 90% of you should have it in your interval there. And hopefully it'll be close to your median as well. So is that true? Do experts usually give these 90% intervals which really do have 90% probability? And the answer is going to be no, I'm afraid. So this is a sort of good news, bad news slide. The plot on the left-hand side is the good news. So the data here that I've used to plot these are based on studies from TU Delft. And they've done, well, at the time, they'd done 45 expert judgment studies in which they'd asked various experts various questions. And the questions that I've taken here are the seed variables that Willie talked about. And so these are questions that in the elicitation, the people conducting the elicitation know the answers to, but the experts don't. So we can test how good the experts are. And in all, there were 67,000 of these. So combinations of different experts and different questions that we knew the answer to. And the experts were asked for a median, a best guess, and 5% and 95% quantiles. And in the left-hand plot here, I've plotted the true values of each of these variables, so the correct answer, against the experts' medians. So essentially their best guess at what these values would be. And then I've got an x equals y line here. So if all the experts were perfect, all the points on here, all the 67,000 points would lie on this x equals y line. And we can see that in general, as the true value increases, the expert's estimate increases. So the expert is giving us some information, which is giving us some knowledge about what values these variables can take. We can see there's a reasonable amount of scatter in the line. Sometimes there's slightly bizarre answers, but overall, that's a fairly positive picture. The right-hand side, though, is slightly less positive. So bin 1 here is all of the variables that lay below the expert's 5% quantiles. Bin 2 is all the variables here that lay between the 5% and 50% quantiles of our experts. Bin 3 is between the 50 and 95% quantiles of our experts. And bin 4 is all the seed variables that lay above the 95% quantile of our experts. And the light grey bars here are if we had correctly calibrated experts who are giving the correct uncertainty bounds, this would be the proportion of true variables that would lie in each of these bins. And we can see that the dark grey bars, which were the actual proportion of these 67,000 distributions which lay in the grey bins, are distributed nothing like the ones that should be if people were calibrated correctly. In particular, far more answers were below experts' 5% quantiles, and far more answers were above experts' 95% quantiles than should be the case. And so this tells us that experts are in general very overconfident. So in general, experts give us intervals which are much narrower than they should be and have much less than 90% probability in them, even though we've asked them for a 90% interval. So when this is an important lesson for people when they elicit, one of our jobs is to try and stretch the experts' quantiles so they're wider than they initially want to give us, because typically experts are far too overconfident in the information they give. Okay, so now let's suppose we've asked an expert for some quantiles and we want to turn this into a probability distribution. Well, how are we going to do that? Well, we need somehow to choose a probability distribution which matches the expert's quantiles. And so let's think of a particular example. So my example is the proportion of symptomatic individuals who actually have a particular virus. So this doesn't have to be any particular virus. So suppose I've taken all the individuals in the population who currently have the symptoms of the virus, what proportion of them actually have the virus? So that's our variable. And let's suppose we asked an expert and they gave us a lower quartile, a median, and an upper quartile of 0.4, 0.45, and 0.55. So they think essentially somewhere around half of these individuals really do have this virus. Well, we want to turn these three numbers into an entire probability distribution. And so one thing that people often try and do is they try and fit some parametric distribution to these three numbers. And if we, in this case, we're thinking about a proportion. Proportions lie between 0 and 1. So perhaps a beta distribution might be a suitable distribution to represent the expert's uncertainty on this proportion. So let's suppose we want to fit a beta distribution. Well, this is going to involve compromise. So the beta distribution has two parameters, and our expert has given us three pieces of information. So it's probably not going to be the case that there is a beta distribution which exactly matches these three pieces of information our expert's given us. So we're going to have to compromise. And one of the ways that people do this, you can do this in lots of ways, is to use least squares. So what I do is I fit a beta distribution which most closely matches these three quantiles that my expert here has given me. And if I do that in this particular case, the distribution I'd end up with for this particular expert is given here. So the blue curve is the beta distribution that's been fitted. The two red lines are the lower and upper quartile, the 25% and 75% point that the expert gave us. And the green line is the expert's median. How well does this fit the values that the expert gave us? Well, the three fitted quartiles of this blue curve are 0.39 instead of the expert giving us 0.4, 0.46 instead of the expert giving us 0.45, and 0.54 instead of the expert giving us 0.55. So it's pretty close. And one of the things we do is report this back to the expert and see if they were happy with the distribution that we fit. So already that feels like quite an involved process to get a single uncertainty distribution from a single expert on a single unknown. But of course, if the question that we're trying to answer is of sufficient scientific importance, we probably don't want to rely on the judgments of a single expert. We probably want to ask multiple experts, as Willie was talking about in his talk, in order to try and get some sort of group view on the values that our input to our model might take. So here's my four experts here, and essentially 4 of the people who are talking this afternoon. And let's suppose I want to ask them for their uncertainty about a particular unknown for a model. Well, instead of having 4 different distributions, 1 for each expert, I may want to in some way combine the expertise of these 4 individuals, coerce these judgments into a single probability distribution. So we can see in the diagram here, each of my experts has their own distribution represented by the red distributions. And instead of taking those 4 distributions, I want to end up with this blue curve in the middle, in some way representing the views of all of them. So how might I go about doing that? Well, there's different ways to do that. So Willie in his talk mentioned the classical method, and this uses a mathematical rule. So I essentially take the weighted average of these 4 red curves here, with the weights given by how well the experts do on the seed questions. We can use a behavioral method, and on the next slide, I'm going to talk about the most widely used behavioral method called the Sheffield elicitation framework. Or we could do some sort of combination of the 2. And there's a couple of examples of that out there. One is the IDEA protocol, which Marissa is going to talk about in her talk slightly later this afternoon. And another one would be some sort of modified Delphi method involving different rounds. But I'm going to talk about a method of combining expert judgments called the Sheffield elicitation framework, which was developed at the University of Sheffield. This is a behavioral method, and it's a method which attempts to try and get the experts to come to consensus about their probability distribution on the unknown. And so it's, in the end of the day, we're trying to get the experts to agree somehow. So this is quite difficult. But the way that it's done within the Sheffield elicitation framework is there's a workshop, and the workshop's represented by this red box at the bottom of the diagram here. And in the workshop, there's 2 stages. So first of all, we perform an individual elicitation, like the ones that I've talked about earlier on in the slides. And that gets me my 4 red curves on this slide here. And then there's a second stage, which is a group elicitation. And in between those 2 stages, there's a discussion between the experts. So we get a distribution for each expert, elicited individually. We display those to the experts. The experts get to discuss why they came to the views that they did, why they've given the distribution they have, discuss why there are differences, why there are similarities between different experts. And then we try to get them to come to consensus and to come to that blue curve on the previous slide, a single view together. Well, of course, they may still disagree, and they probably will still disagree to some extent about the values that our unknown could take. So how can we get them to come to consensus? Well, we use a tool called RIO. And the idea here is that they're not actually trying to get a distribution that they all agree with, but instead they imagine that there's somebody been sitting in the corner of the room and they've listened to the discussions that have been had, they've understood all of the arguments that were made, but they didn't have a strong opinion coming into the room. And what would they think? What would the rational impartial observer, which is what we call this person, what would they think about the uncertainty distribution for that unknown, having seen all the evidence and heard all the arguments that would be made? And the blue curve on that previous slide would represent RIO's probability distribution for the unknown. So this is how the workshop would work in a Sheffield elicitation framework. So that's how this red box in this diagram here would work. But this diagram implies there's lots of work to do before we actually perform the elicitation. And this will be true of any technique that we use. So what are the sorts of steps that we go through before we actually perform the elicitation, ask the experts for their uncertainty about some quantities themselves? So I'm going to talk through that process, the process and the rest of that diagram in terms of an application that I've worked on. So there was a company that came to us and they developed a new diagnostic test for a chronic condition, a chronic lung condition, COPD. And it was a bit like a pregnancy test in that it was a urine test, essentially, and there were some biomarkers. There was the weed on a stick, essentially, and then you got some sort of diagnosis based on the levels of biomarkers in the urine. And this company wanted this test to be adopted in the NHS, but there were different places that you could use it within the NHS process, and it wasn't obvious where the best place it was to put this diagnostic test within the NHS. So they developed a mathematical model in conjunction with us in order to work out where it might be best to put this test within the NHS. And as part of that mathematical model, we needed some parameter estimates, some estimates of our input parameters to that model in order to run the model and see what the outputs would be. And so we conducted an expert elicitation using the Sheffield elicitation framework in order to get our uncertainty distributions on these input parameters to this model. So that's what we did. We performed an elicitation. And so I'm not going to talk about the elicitation itself. I'm going to talk about essentially what was required in order to get to the stage where we could perform the elicitations. So the pre-workshop tasks, well, first of all, we compiled what's called in Shelf an evidence dossier. So the idea here is that you compile all of the quantitative information that's available on the things you're going to elicit about before the elicitation, and you give that to the expert. So they've got all of the data that you could possibly have that's out there at the moment about the quantities you're going to be asking about, so that they know as much as there is to know. And so in this case, there were some reports on COPD in the literature. We had some data on essentially the sensitivity and specificity of the test. How good is this diagnostic test? And we had some data on COPD from national databases. You then put together the elicitation team. So we had a client who were the company. We had a coordinator who organized the workshop. We had a recorder who wrote down everything that was said, all the justifications that were made in the workshop, but crucially not who said them. The experts get the right to essentially be anonymous. So we know who the experts are, but we don't attribute individual statements to individual experts. And an analyst who fitted distributions live in the session. So the experts could see the probability distributions that had been fit based on the values they gave. And we also had an advisor who essentially translated between medical speak that the medical people were talking about and statistician speak that the statisticians were talking about, because we all speak slightly different languages. And so we needed someone to bridge that gap, and a facilitator who actually performed the elicitations from the experts. We also then had to identify and recruit experts. This was early in the development stage of a diagnostic test. There wasn't much money available. There wasn't much time available. It wasn't regarded as a sufficiently important scientific question that we needed a very large panel of experts. And so in this case, we just had 2 experts in the workshop. We had someone from the Academic Health Sciences Network and a senior GP in Newcastle hospitals. So this company was based in Newcastle. And then the experts also contributed evidence to this evidence dossier. So in front of them, as well as the evidence from above, they had details of an audit of COPD patients in Newcastle, data from Quality Outcomes Framework, and also some data on COPD patients within a particular GP surgery. So some partial data which gives some information, but not enough that you could use it to specify parameters in the model. We also had to do some training before we actually asked the elicitation questions in the workshop. So our experts were doctors, they weren't statisticians, and so we had to explain to them what we meant by probability, and we had to explain that it's not just the percentage of coins that come down heads out of the number of tosses of coins that we have. We mean subjective probability, and also the basic structure of the model and conditional probabilities. No problem, Phil, I'm almost finished. And so we had quite a lot of work to do so that they understood the questions we were going to ask them, so they could give us judgments about them. And then in the elicitation session, we asked for medians, 5% quantiles and 95% quantiles for each quantity. But once we'd explained what they were at the beginning, for the rest of the session, we described them as best estimates for the median and surprise limits for the other two quantiles. So the values, you'd be surprised if it was below this or surprised if it was above this, as a shorthand for those 3 quantiles. And the sort of outputs we got from that were conditional probability tables like this. So I'll just go through the bit in red before I move on to my final slide. So for example, here, we imagine the diagnostic test is in use. We're imagining the patient is really having an attack of COPD. And we're asking, well, what proportion of patients in that situation would diagnose themselves as having an exacerbation, would really think that they were having an attack? The experts' median here was 90%, and their uncertainty, their surprise limits were 80% and 97%. And we had to do this for a number of probabilities in a few of these tables. So as I said before, I have some slides on eliciting model structure, but I don't have time for them. They're there if anyone wants to read them later on. But I'll just finish off by going through this slide here and bring it back to infectious disease modeling. So why have I been talking about eliciting these uncertainty distributions on parameters to models? Well, because uncertainty quantification is absolutely critical in situations where we do have quite a lot of uncertainty. And in real-time infectious disease modeling, as a pandemic is moving through the population, we will have lots of uncertainty, and we need to take this into account. This should go further than simple sensitivity analysis, where, for example, we increase and decrease each parameter by 5% and see what effect that has on the outputs. That's not good enough when we have lots of uncertainty like these sorts of situations. And that's because decisions should be taken with an understanding of the uncertainty in the modeling. So it's not good enough to give decision makers a single prediction from my model and say, this is what will happen if you take this decision. There's lots of uncertainty about what's going to happen, and proper uncertainty quantification is necessary to inform decision makers about that uncertainty. And in the absence of high quality comprehensive data, expert judgments must have a role to play in this, because in some sense that's all there is other than underlying physical models and data. And then we can do clever things like Monte Carlo simulations, as again Willie talked about earlier on, in order to propagate that uncertainty through to model outputs. And the final point I'll make, having gone 35 seconds over, is that all I've talked about, and actually most of what Willie talked about as well, is parameter uncertainty, so the uncertainty on parameters in models. We've not touched on model uncertainty, and that's an important element of this as well. The answer from a model tells you about the model. It's not what will happen in the real world, and we should be thinking about the uncertainty between our model and the real world as well. Right, thanks, Phil. I'm done.
Thank you very much indeed, Kevin. That's great. We've okay, we got 2 or 3 minutes for questions. There are a couple that have been posed. So Robin Hanson asks, Shelf sounds a lot like the old Delphi method. Can you elaborate on the differences?
So in Delphi, typically there's a lot more, so typically it's not done in one room with all of the experts present at the same time. Typically it's done with the experts not co-located, and there's some sharing of information, but that sharing of information is essentially done by the person running the workshop. So essentially you would report to all of the experts back the individual elicitations, but the experts wouldn't know who said what, and they wouldn't get to discuss directly between themselves. That discussion would essentially be drip fed. The information from each expert would be drip fed to all of the rest of the experts. And so they wouldn't get an interaction within a particular room at the same time, talking through the issues themselves. And then in Delphi, the idea is you have different rounds which try and bring you to consensus, but you don't get the experts to discuss and essentially elicit a consensus distribution in a single occasion. You essentially try and have rounds and gradually bring the experts closer together. But at the end, if the experts still aren't together, you would then impose some sort of mathematical rule, which you'd never do in Shelf. So it's a different sort of process. Shelf is completely behavioral. Delphi involves rounds and less direct contact between the experts.
Okay, then there's one more question quickly from Mark Bergman. Other questions we'll handle later on. Do you try to take advantage of group diversity in terms of worldview, cultural background, styles of reasoning, etc.?
So that's partly a question of recruitment of experts. So you will try and recruit a diverse panel of experts, as diverse a panel as experts as you can. Often in Shelf elicitations that I've done, there have been experts who have been essentially more expert in certain areas than other experts, and all the experts in the room have known about that. So you might have a lot of vets in a room. That's the vet specialist in cows, and so if there's a question about cows, everyone sort of listens to the cow expert to some extent. And so Shelf allows for that, because the experts get to talk to each other about where their evidence comes from, what they're basing their views on. And so experts will sometimes defer to the one who knows more about that particular area. And sometimes experts don't agree. So sometimes I've not ended up with a single consensus distribution. I've ended up with 2 consensus distributions, because there's 2 different scientific theories. If one's true, this is going to be the uncertainty distribution. If the other one's true, this one's going to be the uncertainty distribution. So you might not always come to a single distribution, but often you can when the experts get to discuss each other. Often disagreements are more disagreements about what the question's asking than disagreements about what the answer is going to be.
That's great. Thanks very much indeed, Kevin.